Hello, y'all. We are going to go through ramps and inclined planes today. So looking at forces in Unit 2, we're going to run into a number of problems where either they're on a ramp or inclined plane, which is pretty much the same thing, I guess. A ramp is a solid object, and an inclined plane would be like a board that's been set up to form a ramp. But they are, for our intents and purposes, they are the same thing. All right, so the objects that are on these ramps could be stationary, they could be moving. Um, we're going to draw a setup or scenario where an object is on a ramp, and we'll talk about a few things as we go concerning whether the object is at rest or moving and the forces that would be acting on it. Okay, so I'm going to draw just an object here, and we're going to identify some of those forces. We're not doing a full-on free body diagram, but we'll still draw the forces acting on our object. Of course, one of them is gravity, and gravity acts straight down. I do find it useful, if I'm drawing an image, I find it useful to have that back side of the ramp there and have gravity just be parallel to that. So we'll do that here. You can see I've drawn my force of gravity, trying to keep it parallel more or less with that back side of the ramp. So that'll be your force of gravity, which is mass of the object times 9.8 or 10 if you're on Earth. Now, of course, there is some normal force from the surface of the ramp, just like a table or floor. The ramp is going to support the object sitting on it. But the really important thing about normal force when it comes to ramps and even something like an object pushed up against a wall is that normal force acts perpendicular to the surface that the object is in contact with. So this normal force is not straight up or opposite exactly to the force of gravity. If it were on a flat table or floor, then yes, gravity would be straight down, normal force would be straight up. So gravity is one of the forces acting. Normal force is another, and we need to make sure that we draw that normal force like so. Now, in a little bit, we're going to talk about and go into more details on exactly how big the normal force compared to gravity is and what's going on with sort of the balancing out of gravity and normal force that we often see when something is just sitting or even moving, sliding on a horizontal flat surface. All right, there's one more force that we would have to consider, and that would be friction. So I'm not, I guess I'll draw a couple options. I'm going to do some dotted lines for these just to indicate that these forces could be present but are not necessarily. My dotted line idea is not working out as well as I'd hoped. Drawing a straight line is a little harder when it's dotted. So we could have friction going up the ramp. And whether it's static or kinetic really depends. If the object is sitting at rest right now and it's not moving on the ramp, then you would, of course, have static friction. If the object is sliding, and specifically if it's sliding down the ramp, you would have kinetic friction. Because we know that friction always opposes the direction that we're trying to move the object or that the object is moving. So if it slides down the ramp, you'll get friction up the ramp. Vice versa, if you have an object that's sliding up a ramp, your friction would have a direction that's down. Now, you're not really going to see a force of static friction going down the ramp because we'll talk about this in a second, but gravity is trying to get the object to go down the ramp, and if we have static friction, it's probably just acting up the ramp then because you'd have to have some other forces involved if you ended up having static friction that was acting down the ramp. So I think we'll almost never see that. So while you could have friction up or down the ramp, depending on your problem, if it says it's a rough surface, you have friction. If it says there's no friction on the ramp, you don't. So that one just depends. Sometimes we will have a force of friction. And it depends on whether it's static or kinetic. Is it moving on the ramp or is it sitting still on the ramp? Okay, now let's talk a little bit about how we're going to set up forces or do a sum of forces or specifically how we're going to look at directions. So it turns out what we want to do with a ramp is for a couple of reasons, what we want to do is we want to reorient this ramp. We're going to put that in here, and we're going to, over here, we're going to reorient the ramp. There are a couple key reasons for this. One of those is that we often want to find what's going on with like the sum of forces or the acceleration, both of those in Newton's second law. If we look at the sum of forces acting on an object equal to its mass times acceleration using Newton's second law, we could say, well, what forces are acting on the object to result in some possible acceleration? Maybe it's sliding down the ramp, maybe it's going faster, or it's speeding up, or maybe it's constant velocity if the forces are balanced. So using those sum of forces to determine, well, what's happening with our object? Is it accelerating, or based on maybe the problem tells us it's at rest, or it's accelerating, or it's constant velocity, and we want to use that information to look at the forces. When we do all of that, we want to be looking at specifically acceleration, and because of that, we want to look at forces along the surface of the ramp. And occasionally, we might be interested to some degree in the forces acting directly into the surface or directly up from the surface of the ramp, like normal force, for example. But for the most part, what we're most interested in is accelerations, forces, even something like looking at the velocity, whether it's speeding up or slowing down, and how fast it's going. We could do that along the surface of the ramp. So is it sliding down the ramp at 4 meters per second? Is it accelerating at -3 meters per second squared as it slides up the ramp? All of those vectors, velocity or acceleration or force, we want to be looking along the surface of the ramp. So if we stuck with our normal directions, just looking at this image on the left, we would have gravity vertically, straight down, and every other one of these forces, friction up the ramp, friction down the ramp, normal force, even something like applied, you could possibly, not often, but you could possibly have someone pushing while it's on the ramp, pushing it up or pushing it down. All of those forces would be angled according to our normal directions. Gravity would be the only one that was vertical. Normal force would be off at some angle, kind of up into the left here. Friction, depending whether it's up or down the ramp, would be angled as well. And what we'd have to do, unfortunately, if we did this, is we'd have to start splitting all those other forces into their components. Because angled forces, we want to be really careful that we are not just plugging in an angled force into a sum of forces in the x or y direction, right? Because just like kinematics with big five, we have to split them off into x and y directions. It's very important in any problem that when we sum forces, we don't just start throwing in all the forces. We specifically look at what are the forces in the x direction, what are the forces in the y direction. When I do a sum of forces, I'm going to make sure that it's x or y. Okay, so in light of that, what we're going to do is we're going to say that the x direction will be the surface of the ramp. And we'll draw that in just a second here. Okay, so it's going to do a couple things for us. Once we draw it, we'll point out how it really helps us on the angled forces front, because right now, as it stands, we would have to we'd have to split normal force and any forces of friction into their components using angles and trigonometry. So I'm going to redraw this ramp. I'm going to have the surface of the ramp be just purely horizontal here, and I'll talk about kind of if you have a piece of paper, you can actually do this. If you don't mind doing your problem by turning your piece of paper, you could do this without redrawing it if you wanted. All right, this going on here. Try to get my lines appropriately. Good. draw. I try to get a right angle going on here. It's a little hard now that I'm at an angle. We'll figure it out. All right, I think that's pretty decent. Something like this. It's pretty much a right angle. All right, so I've redrawn my ramp, or rather, I've reoriented my ramp. So I basically took the whole thing. You could picture taking the entire ramp, and if you could turn it on the page, we'd just like rotate it clockwise a little bit here. So rotating the whole image of the ramp clockwise, we end up now looking at the surface of the ramp as our x direction. Okay, let me draw our object again. We'll draw some forces, and then we'll actually get into how we work with these forces. All right, there's the object. Let's draw our force of gravity, making sure that I draw that gravity parallel to the back side of the ramp. It can be very helpful to have this so you can try to make sure that your gravity is parallel to that. I want to make sure I include an angle as well. So whatever theta is, could be a 30-degree angle or 25 or whatever it is at the bottom of our ramp there. Usually that's what they give you is they say a ramp or inclined plane is inclined, 32 degrees above the horizontal. So that angle at the bottom of the ramp is typically what they'll be giving you as far as angles are concerned. All right, let's draw our normal force. So... And then friction, if friction is present, it would be one of these two, left or right. Because now our left and right are just along the ramp itself. Okay, we're not going to worry too much about friction. If it shows up in your problems, then use the friction equation or look at the normal force or the mu value, and that's going to help you deal with any friction that comes up, right? So things like the coefficient of friction, mu s or mu k, along with the normal force, are the equation we'll do for friction. But I want to specifically focus on gravity in a little bit here because normal force and friction are now vertical or horizontal forces. That's really the other thing that we accomplished. Not only does reorienting our ramp allow us to find an acceleration in the x direction or a sum of forces in the x direction that is along the surface of the ramp, which is what we want. Because if we solved for an x acceleration in this previous picture, what we'd get is we'd figure out what the acceleration is like in this direction. And that's just not super helpful. We don't really want that. We don't want to know how much it's accelerating like out and away from the surface of the ramp at some angle. We want to know what is the acceleration or the net force or one of the forces acting along, up, or down the surface of the ramp. So we've accomplished that. Our x direction allows us to sum forces directly up or down the ramp, and that's our x direction sum of forces. In the y direction, we have normal force. Now it's instead of looking like it's angled from the surface of the ramp, it's straight upwards according to our reoriented directions. And we'll just add a reminder that we could pick whatever directions, like positive could be up the ramp and positive could be directly out of the surface of the ramp. Or sometimes a problem will tell you what directions to pick. Okay, so where this leaves us is that the only angled force, according to our reoriented ramp, is now the force of gravity. So we've saved ourselves doing angled forces on normal force and friction and any other force acting directly up or down the ramp. So the one force that is now angled that needs to be split into its components before putting it into a sum of forces is gravity, which is kind of weird because we're used to gravity being just straight down because we haven't reoriented our directions on any other problems. I guess we sort of did it for Atwood's machines where we said we're going to use clockwise and counterclockwise for directions rather than left, down, up, right. Yeah, so gravity is the force that we have to split into its components. So let's talk a little bit about what that means for gravity to have components. So partially, gravity is pulling the object directly down into the surface of the ramp. That is part of what gravity is doing. So one component or part of the force of gravity is that that it pulls the object into the surface of the ramp. So we'll do a component that we're going to call FGY, splitting gravity into its two parts. The other is gravity does pull the object down the ramp. So the two things gravity is doing, the two components, gravity is pulling the object into the surface of the ramp, which is then balanced exactly by the normal force. And gravity is pulling the object down the ramp. Now, it's worth noting as well, if there were any other forces directly down into the surface of the ramp or any forces directly up off of the ramp, that would affect normal force. So just like all of our other scenarios, gravity is usually, or often, but not always equal to normal force. We just need to check and say, if gravity is the only thing pulling our object into the surface, then the normal force will equal gravity. If there's other forces pushing down into the surface or up off of the surface, then normal force will be different. It will sort of adjust itself to be as large as it needs to be to balance out all those forces into the surface and away from the surface. All right, this is FGX over here. So the X component that is along the ramp, FGX is the part of gravity that is pulling our object down the ramp, trying to accelerate it down the ramp. Okay, so how do we find these? Well, we are going to use that angle theta, but it's a little weird to figure out what it is, but we can do it here. So I'm going to draw a couple other angles. This angle here is 90 minus theta. And we know that because I've actually created another smaller right triangle with the force of gravity here. I did draw the force of gravity intentionally all the way to the bottom of the ramp here just because I wanted to get the visual of gravity X straight down. So angle-wise, we've got the angle at the bottom of the ramp, whatever that is, could be 30, 20, 40 degrees, whatever it is. And then we've got a 90 right here. We got another right triangle. And this one up here is 90 minus theta. That means that this angle right here, I'm going to sneak it in there. There's the blue angle. That must be theta. I'm going to make that a little bit bigger. Okay. So the blue angle that I've drawn is theta because, okay, let's kind of talk through it. There's a lot going on. You don't have to memorize or know the process by which to find the angles here that we're using for sine and cosine to find FGY and FGX. I'll show you an end result that you can always use, but I just wanted to show a little bit of how we get there. So knowing that we have one right triangle here at towards the bottom of the ramp where FG, the purple force of gravity, is sort of making a smaller version of the right triangle we have for the ramp. We have theta, we have 90 minus theta, and then the green FGY component of gravity, of course, makes a right angle with the surface of the ramp because FGY is the component of gravity that's pulling directly into the surface of the ramp. So this, the red plus blue angles is 90. And if this is 90 minus theta, then the blue angle we've identified here is the same exact angle as the one at the bottom of the ramp. Okay, so that allows us to actually find FGY and FGX. We do them exactly the same way as we would any other angled force. We have a right triangle with the purple hypotenuse and the two green sides with the blue angle. And that is, well, let's write it out. So FGY is adjacent to the angle theta. Now this one's a little bit weird because normally in all of our other sort of angled force problems, we had been, even as far back as Unit 1 with projectiles, we had been using sine for y and cosine for x. That was typically how it ended up being almost all the time. With ramps, it's tricky with gravity, not only because we have to think about gravity differently and say we're going to split gravity into parts, and part of gravity pulls into the surface of the ramp, part of gravity pulls down the ramp to try and get the object to accelerate down the ramp, depending what other forces are acting there. Um, but FGY, we're going to use the cosine of theta because FGY is adjacent to the blue angle theta there, or the same as the angles at the bottom of the ramp. So cosine theta times the hypotenuse, Fg, the total force of gravity, gives us that y component. Same thing for x. X is actually opposite to the blue angle theta there, so we're going to use sine theta times Fg. Okay. So, sorry, just to kind of recap where we've been. We decided to use directions as x direction being along the surface of the ramp. So our x direction is along the surface so that we could find the velocity, acceleration, forces, any vectors, even displacement, how far it goes. We want to look at that acting along the surface of the ramp. And the y direction that we've chosen is perpendicular to the surface. So we made sure that then the normal force is a y direction force. Any amount of friction is an x direction force, and gravity was the only one that we split into components. To find those components, right, we have to use trigonometry, but it's a little tricky to go from the angle at the bottom of the ramp to what are the angles in this right triangle we've got for gravity, but you can get there. Again, I would not recommend going through this entire process of drawing all the little things here of like, okay, I'm going to draw my gravity all the way to the bottom of the ramp and make sure it's parallel with the back, and then identify that this is 90 minus theta, and then do some geometry type stuff to get the angle theta here. Instead, I would just say, if you know the angle at the bottom of the ramp is theta, which is almost always what they're giving you in a problem, is saying here's the angle like that the ramp is inclined above the horizontal, then simply use this, or this would be the thing to memorize. Now, these aren't on the equation sheet. The specific x and y components of gravity when it comes to a ramp are not something on the equation sheet, but to know them is going to be important because any ramp problem that we encounter, anything on an inclined plane, we're going to want to either like visually on your paper. If you're working on your paper, you could turn the whole thing clockwise. You don't even have to redraw the ramp. You could just turn it. So now you're looking at the surface of the ramp like this, where it's horizontal. But you want to acknowledge then, I'm going to have to split gravity into parts and say, in the y direction into the surface and out of the surface of the ramp, as well as the x direction along the ramp, I need those parts of gravity. So I can put FGY into a sum of forces for the y direction, although that's less needed or less common to use. And I can put FGX into a sum of forces for the x direction along the ramp, whether there's friction or anything else or any other forces there. Okay. Yeah. So these are worth memorizing just because A, they are different from the other sine and cosine for angled forces that we've used. And even back in Unit 1, when we did sine and cosine for angled initial velocities when launching a projectile. Because normally we do cosine for x, normally we do sine for y, but the way the angles work out here, it is switched. It is the opposite. We use the cosine of the angle theta that's at the bottom of the ramp to find the y component of gravity, and the sine to find x. Or you could think about it as sine theta will find you the component of gravity that is pulling down the ramp, down the surface of the ramp, and cosine theta rather will find you the component of gravity that's pulling directly into the surface of the ramp, which often is equal to normal force unless there were other forces acting in our y direction that we've drawn in the reoriented ramp. Okay, so it's kind of a lot to change up the directions, reorient the ramp, and then have to, from there, split up gravity of all things, where gravity, of all the forces, we're like, gravity is just, it's a y direction force, right? It's always vertical, it's always straight down, it's always towards the center of the earth. we're very much not used to having that be like an angled force. Um, but with how ramps work out, it is. So that's the main tricky part about them. They can be really tough to get kind of figured out because you're splitting gravity into parts, and those parts of gravity are not the typical sine and cosine. They're switched from what we normally do, but it's important. There's a couple other comments would be Atwood's machines. You might have there could possibly be an Atwood's machine where one of the objects hangs off the back of the ramp over a pulley and the other one is on the surface. So keeping in mind things like tension in a string for an Atwood's machine could be pulling, even if it's not an Atwood's machine, there could be a string attached to an object that's being like pulled up the ramp or something like that. So just keep your eyes out for that, where if there's friction, if it's a rough surface of the ramp, you'll have friction either up or down the ramp, just determining like what's happening with the object. Is it sitting on the ramp and gravity is trying to get it to slide down, but maybe static friction holds it in place with static friction acting up the ramp? That's possible. Is it sliding up the ramp? Maybe somebody pushed it up the ramp and they're no longer applying a force. That's another thing is if it says that someone shoves something up a ramp, like they give it a push at the bottom, while it's sliding up the ramp, it won't have applied force acting on it while it's going up the ramp. So there's a few things that come up here and there in problems. Most of that we'll get into when we actually solve some AP questions, and we'll deal with ramps as they come up in the problems. But the really big thing is being able to reorient the ramp, switch up your X and Y directions. And when you look at a sum of forces in the X direction, that's along the surface of the ramp. When you look at a sum of forces in the Y direction, that is into the surface of the ramp or directly up out of the surface of the ramp like normal force here. Okay, we're actually not gonna add really anything else to this video because circular motion is a piece. It's sort of a separate unit that AP does apart from forces, but I think it has a lot of really important ties to forces, and there's some things like orbits and gravitation that we can really look at there. So we are gonna finish Unit 2 with circular motion, but I'm not gonna start that in this video. So this will be a little bit of a shorter one, but an important one nonetheless, because any problem involving a ramp, we will need to be able to look at the directions a little bit differently in order to find acceleration or forces or whatever we're being asked to find, some vector going down or up the surface of the ramp. We have to sort of reorient things and then be able to find components of gravity using trigonometry. Okay. We'll do some ramp problems in class. We'll look at how to do this, whether we're plugging in numbers, maybe we're deriving equations. There can be some tough ramp problems where you're doing deriving and you have to, in your equation with variables, you actually have to do the cosine FG and the sine FG, or this could be, they often write force of gravity as mg, right? Because it's mass times 9.8 or mass times 10 on the Earth. So mg is a common way to write force of gravity. So you'll see like cosine theta mg and sine theta mg for ramps. Yeah, so we'll try and get some examples and practice problems and all that good stuff. Because while they weren't on the quiz, ramps will certainly be on the test. You might see one or two problems involving those. And there's plenty of them running around in AP Classroom and on the AP test itself in May. You could find some of these. Okay, well, that'll pretty much wrap it up for ramps, but we'll be back for circular motion, which is difficult in its own way. I think both ramps and circular motion can be tricky to kind of get behind the way that we're doing it, or like the reorienting of the ramp and the splitting of gravity, along with some of the concepts behind how circular motion works can feel a little bit weird. So hopefully we can take the time to bring any questions. If you have questions about ramps, if you have questions about circular motion and how we deal with them, put those in the Padlet for anonymous questions or bring them in class, and we'll see you then.